Dear students, now I am going to find the relation between the linear velocity and angular velocity. Relation between linear and angular velocity. So let us consider one particle is moving in a circular path like this. It is center of circle. Okay. So the particle is moving in a circular path with a constant angular velocity omega in the anti-clockwise direction, in the anti-clockwise sense like this. So in a small time interval dt, this particle describing the smaller arc length, say the smaller arc length is ds. In a small time interval dt, the smaller arc length described by this particle is ds. So the corresponding angular displacement is also very small, that is equals to d theta. Clear? So though it is moving in a circular path, if I consider a small time interval, this arc length will be like a straight line. So I am writing this is the smaller angular displacement ds. Yes. Here the tangent drawn to the circular path gives the direction of velocity of the particle at that point. So this I am drawing a tangent to the circular path here. This gives the direction of linear velocity of that particle. Now I am going to find the relation between this linear velocity and angular velocity of this particle. So let us see. From this information I can write this angle, smaller angle d theta is equal to arc length ds by radius r. So let small r be the radius of the circular path. So after rearranging I can write ds is equals to d theta into r. Yes, this is the small angle arc length ds is equals to d theta into r. So differentiating with respect to time on both sides, so I can write ds by dt equals to d theta by dt into r. So r is a constant. Why? When the particle is moving in a circular path, this radius does not change. So this r is the constant term. Need not to write the differentiation to the term r. Now we know ds by dt is the rate of change of distance. This is called speed v equals to. So this is omega into r. So d theta by dt, here ds by dt is equals to v, d theta by dt equals to omega. This is the linear speed, this is the angular speed. Now this relation gives the link between linear velocity and linear speed and angular speed. This is the relation between linear and angular speeds. Right. So this is the scalar form. Now let us find the relation between v and omega in the vector form. In vector form, so I can write ds vector is equals to d theta vector cross r vector. So this is what a small displacement vector equals to small angular displacement vector cross r bar. R bar means this is the position vector. So let us again differentiate this equation with respect to the time. So differentiating with respect to time, what will you get? ds bar by ds vector by dt is equals to d theta vector by dt cross r vector. Again this is a constant, so I am not writing any differentiation, means I am not expanding it, right. ds vector by dt equals to velocity vector, this is linear velocity vector, and d theta vector by dt equals to angular velocity vector. Now this equation changes as v vector, v bar is equals to omega bar cross r bar. Yes, this is the linear velocity, this is the angular velocity, this is the position vector of the particle or radius vector of the circular path. So we know that this is the relation between linear velocity and angular velocity, right. So v bar is equals to omega bar cross r bar. So if you observe this expression, so omega bar, r bar and v bar are perpendicular to one another. How? Suppose you see, suppose a particle is moving in a circular path with a constant angular velocity in the anti-clockwise sense like this, and this is the position vector r bar, okay. So this is the, if I take any point to know the direction of linear velocity at this point, I need to draw a tangent like this. This gives the direction of velocity. So we know it is appearing clearly r bar and v bar are perpendicular to each other. So what is the way to know the direction of the angular velocity? Yes, to know the direction of, we know already in the previous class we studied the how to find the direction of the angular velocity. So when the right hand fingers are curled in the direction of the rotation, the thumb indicates the direction of the angular velocity. So the direction of angular velocity omega will be like this, means perpendicular to the plane of the board coming out. So if I take the direction of omega like this, so omega is perpendicular to r, okay na, omega also perpendicular to v, that means all are perpendicular to one another. Now how to find angular velocity of a particle, right. Suppose so this is the point, O is the point which is at rest, fixed. Now this is the P is the point, a particle which is moving with a velocity v like this. Yes. So I want to know what is the angular velocity of the particle P with respect to this fixed point O. Yes, we know one formula for angular velocity. What is that? From V bar is equal to omega bar cross r bar, I can write one thing. Omega is equals to V perpendicular mod V perpendicular by r mod r bar perpendicular. So by using this relation we can find the angular velocity of the particle. So what is this? Mod V perpendicular by mod r bar perpendicular. V perpendicular means the perpendicular component of velocity. Mod r bar means what? This is the magnitude of the position vector, right? Yes. So to know the angular velocity of the particle P, let us first draw the position vector of P with respect to O, like this. So I am drawing a position vector like this. Yes. The first step. The second, we have to resolve this velocity into two components. So one component is parallel to the position vector, other component is perpendicular to the position vector. So if I resolve this velocity into two components, this is V parallel. Now this component is V perpendicular. This is the V perpendicular, right? If you observe these two components of velocities, this component V parallel, the parallel component of velocity cannot bring this particle into a circular motion about this fixed point. Why? This V parallel is acting like this, so it cannot bring this particle to move in a circular path about this fixed point. But if you examine this perpendicular component, it can bring this particle to come into a circular path like this. So here this is the component which will bring it into a what? Circular motion. So you see that omega. Now omega is equals to, what is V perpendicular? This is V perpendicular by, suppose the position vector of particle with respect to the fixed point is say r. This is the r, V by r. The perpendicular velocity is say V perpendicular by r. I am not writing in the rectangular components form, means cos theta sin theta form, V perpendicular by r. So what is the direction of this angular velocity? If you observe this, it is the magnitude. So to know the direction of angular velocity, we have to curl the fingers in the sense of rotation, means this particle wants to move in a anti-clockwise sense. If I curl my fingers in the anti-clockwise sense, this stretched thumb gives the direction of the what? Angular velocity. Now let us assume this is the x direction, this is the y direction. Now what is the direction of angular velocity? Yes, this is the direction of angular velocity. The direction of angular velocity is perpendicular to plane of x axis and y axis, like this. So it will be along the positive z axis. What is the unit vector in the direction of the positive z axis? That is equal to k cap. Like this you can find the angular velocity of a particle. Let us find one more example. So the example is a particle is moving with a constant speed in a circular path as shown in the figure. find the angular velocity of a particle with respect to fixed points B and C, given the angular velocity of P with respect to fixed point O is omega. So the diagram is like this. It is also part of question, right? It is a fixed point O. So this is circular path. It is the particle P which is moving with a constant speed like this. Yes, it is the one more fixed point B and one more fixed point C. The distance between B and C is R. Yes. So we have to find out what is the given question. A particle is moving with a constant speed in a circular path I shown in the figure. Yes, it is moving in a circular path with a constant speed. Find the angular velocity of the particle with respect to the fixed point B and C, given the angular velocity of P with respect to the fixed point O is omega. So what is given? First let us find the angular velocity of P with respect to O. Yes, this length is again R. Yes, when you come to solution, yes, so angular velocity of P with respect to O, velocity of P with respect to O equals to velocity of P with respect to O perpendicular by R. So what is this? It is a point P, it is the fixed point O. Let us draw the position vector of P with respect to O like this. Yes. What is the velocity perpendicular to this position vector? Yes, this is the velocity which is perpendicular to the position vector. So in the place of VPO perpendicular, you can write V by R. R is the distance between P and O, that is equal to R. This is given as omega. Now let us find the angular velocity of P with respect to B. Yes, angular velocity of P with respect to B. So listen, this is the point P which is moving with a constant speed like this. This is O, this is another fixed point B. Yes, you need to find the angular velocity of P with respect to B. So let us draw the position vector of P with respect to B like this. Draw like this. What is this total length? We know this length is R, this length also R. The total length will become 2R. The total length will become 2R. Now omega PB equals to, what do you write? Velocity of P with respect to B, but this is the perpendicular component, by RPB. So what is the meaning of VPB perpendicular? The component of velocity which is perpendicular to the position vector. Yes, it is the position vector. This is the position vector, this is perpendicular to the position vector, this is the VPB perpendicular. So I can write this is V by RPB, the magnitude of the position vector, which is equals to 2R. Yes, we know already V by R is equal to omega. So V by R, 2R. So you can write omega by 2. Okay. Finally, position vector, angular velocity of P with respect to C. You need to find the angular velocity of P with respect to C. Once you see, so what is the, let us draw the position vector of P with respect to C. Yes, this is the position vector of P with respect to C. What is the magnitude of this position vector? R plus R plus R. This is total 3R. The total is 3R. Yes. Now this is the velocity which is perpendicular to the position vector. So angular velocity of P with respect to C is equal to linear velocity of P with respect to C, which is perpendicular. We should take perpendicular component of velocity of P with respect to C by RPC. So what is this? This is equals to V and this value is equal to 3R. Already it is known the value of V by R is equal to omega. This is omega by 3. So in all the cases, what is the direction of angular velocity? So let us place our right hand like this in such a way that fingers and thumb are perpendicular to each other. When I curl the fingers in the direction of motion, the thumb is indicating the direction of the angular velocity. This is pointing out of the plane of the board, which is equals to k cap. So in all direction, the angular velocity, in all the cases, the angular velocity is directed along the positive z direction. So which is represented by the position vector means k cap.